Hi, in this video we'll discuss about the icing formation on any aeroplane, maybe missile or helicopter that is flying high at particular altitude in the clouds. So in the clouds, there can be a water droplet of very minute diameter like 20 microns or 10 microns in a subcooled state. So subcooled state means it will be like below 0 degrees centigrade and still it will be in water format. The main reason for this format in water is due to the lack of nucleation. So ice, in order to form an ice, we need to have a point or a surface in which nucleation can occur. And this low diameter cannot easily converted into ice. So that's the reason why they still form or they still being observed as a droplets of subcooled water. I mean, it will be like minus 20 degrees centigrade or minus 30 degrees centigrade high in the altitude in the clouds, right? So when an helicopter or a missile or anything that so enters into this atmosphere, these particles try to adhere onto these surfaces of the aeroplane or missile, and they start as a nucleation site on which these water droplets grow more and more, and it will turn into ice due to the freezing point that it's like obviously at atmosphere it will be 0 degrees to your freezing point. So as it is already at minus 20, it will turn into ice and it forms an ice layer over this missile. So as it forms an ice layer over a missile, obviously the mass of the missile increases or the mass of the helicopter aeroplane increases, and as well as the aero surface, what exactly for dynamics. So the aerodynamic surfaces completely will be erased. So then there will be high fuel consumption. It will not go along the track what it is decided to be. So we need to take care of all these situations. So now I'll try to explain this formation of ice using Ansys fluent icing model, how exactly it forms. Okay, so now this is the model what I am trying to take, and I'll just create an enclosure for this. I'll go here and I'll just select design sketching. This is just an example, so it will not be to actual methodology what it need to be drawn, and we also need to fill these small things. So it is a small replica of a BrahMos missile. So I've filled those gaps. Then we'll be going into the structure, the design. We'll draw some design onto it. Second, turn this properly. Yeah. Mhm. Maybe I'll take some replica of the surface. Okay. And the shape, maybe I'll consider this way. Okay. Same line, we'll try to mirror it. Select this and mirror. Okay. Now we'll draw, close this. Okay, I will trim these things. I think this is also not required. I'll be selecting in this way. Hope this will be fine. pull, click on symmetry, no merge on either of the sides, 1000. Okay. Now we will try to remove that missile. It's not required. We need to have only the walls for our simulation. We'll remove that. This and this are not required. Delete those. And this is the fluid. Rename it fluid. And we'll select, go to the groups, and this will be our inlet, and remaining everything will be outlets. So we'll just select everything apart from that, and we'll give outlet, and we'll select this face and control A. So we'll be selecting 70 faces. We'll remove the remaining faces except the inner missile faces. Okay, and now we'll create as a wall, because on that wall only we'll have the ice formation. Now we'll just minimize this, go to the workbench and double click on the mesh, and we need to have tet or hex mesh. Poly mesh is not supported in this kind of scenarios. Okay, start. So we'll try to read the geometry into the fluent meshing, and we'll create a tet mesh below 1 million mesh count, because to the student version what we are working on. Import geometry, import, update, no local sizing. Surface mesh I'll be selecting 4, and here in the curvature proximity I'll select curvature with 30, go up to 5, check. Okay, and here we'll select 9 layers, selected labels, wall, uniform, will increase up to 5, and it will be maybe 1.04. The growth rate should not be very abrupt. Go to volume mesh, here it should be tet mesh, tetrahedral, select 1.05 and generate volume mesh. So we got a mesh more than 1 million, so we need to reduce it. Maybe I'll go here and edit it, and I'll keep it as 6 and 6.5. You just check, update, describe, apply. Oh, sorry, here we need not want this geometry. We'll just select this we not want, so we can keep it dead, because that is the internal part of Brahmos. I'll try to edit, make it dead, update, and now check whether it is million or not. Sorry, below 1 million or not. Yeah, it's below 1 million. Now, okay, we'll just check. It's very coarse, but we are limited to the node counts, right? Let me see. It's very coarse. Yeah. Okay, it's only for demonstration purpose. We'll be taking this. Switch to solution. Yes. So we'll activate gravity. We just want to have the gravity also. So it will be in minus 9.81 direction. And we'll on the model for energy. And instead of k60 k omega, we'll take k epsilon. It's realizable. And in the boundary conditions for inlet, it will be around inlet. We'll take it as an 80 meters per second. The temperature of the ice, we'll take it as a 260. Temperature of water, the air present in the surrounding, we'll take it as 260. And these things, we'll take it as a pressure far field. It's not reasonable, but so we need to identify. Okay, anyways, we'll try to select a pressure outlet only because it's not too far from that and it is not correct if you take pressure far field. And here at backflow, we'll take 260 only. The pressure far field is the correct one, but as the mesh count is limited and we cannot have a huge domain, it should be very huge in order to have the pressure far field. And we need to try to assign the same outlet condition to everything. Copy to all this copy. Yes. Everything now will have obviously 260 in the temperature or thermal boundary. Okay. And in the fluid wall, we'll go and edit. So that is the internal part of the BrahMos missile. We'll take the temperature as maybe 278. Okay, close it and now try to save this case. Right, sorry, export case. Maybe I'll save it in icing module only. It should be saved in the case GZ. So famous dot case dot gz. Okay. Now after the saving, you'll just close this and open a new Fluent with icing module activated. So now I'll close this. After it is closed, we can use a Fluent module. Click on the setup. Maybe with we need to have this. Okay, in standalone, we'll just check 1 second. Yeah, the icing. Click on start. Now try to create a new directory for that. We use in the icing only. I'll create a name, Brahmos. This is the project name, and you can import the case file what you have said, the bremos.case.gz. Click OK. It will take some time to load, and we are using only 4 cores because it's in student version. The fire higher the ice formation, I'm taking some non-existing conditions. But if you want to take the existing conditions, I'll just show it to you in the droplet section. Okay, so now just verify. So all the settings what I've taken is from Fluent only. So if you can click here on this Fluent module, you'll be seeing case settings. But if you want to name by yourself, then you can go to Air and you can just modify all these things. But I am right now I'm taking from case settings, or the settings what I have considered in the face, or sorry, Fluent. So, and I just want to activate all the modules. So I've clicked all three. So first I'll be going with Fluent module. I mean the simple layer flow. After that I'll activate the droplet, and then I'll go with the ice formation, right? So it is like a step by step. First the fluent airflow, next the droplet module where there will be a water droplets of micrometers which cannot be nucleated into ice due to its suspension inside in the air, as it don't have any nucleation sites. So when it comes in contact with this surface of the bremos, it will start nucleating and the ice will start forming. Okay, so these are all the conditions what you have got from the Fluent case setup only. You need not worry. So go to the airflow, and now I'll be maybe selecting 250. It's only demonstration purpose. So click on initialize and then click on calculate. So I initialized. Now you can click on calculate. It will take some time. So maybe it will come after some while. So after the run is completed, I'll be just going to droplets and I'll increase this liquid water content. Actually, it is not the correct value, but if you want to have that, you can just go edit here. Then you will be getting these intermittent cumuliform cloud or stratiform clouds, and where you can mention the air temperature. Accordingly, you will be getting the LWC with respect to the altitude. I'm not considering those. I'm taking a random values where I can see more water content inside the cloud. So I'll click enable. Go to the droplet velocity vector. I'll be giving here 80, and go to particles. I'll be selecting maybe 200 iterations would be sufficient. It's only demonstration. Calculate. Okay. So we'll come after some time again. Yeah, so now the particles are injection is completed, and the residuals you can see it then came down. Now we'll go to the ice module, and we'll give the relative humidity as 80%. So 80% of the air is completely filled with water. We'll activate the beading, and now we'll go to the ice, and maybe we'll run for 1000 seconds, and we'll just check how the ice has been formed. I'll click on calculate, and these two also will take time. So now I've just activated a counter after the ice run is completed. Now you can see this is icing, and I've selected ice thickness, and I have selected the wall, and I'll try to collect the display. So this is the value what we got. We can increase the or decrease the maximum value so that you can see ice formation more where exactly is happening. So these are all the ice formation zones that are tend to happen. Okay, so you can see these are all the ice formation zones, but you need to refine much more in order to have an accurate value. But out of computational resources as well as the mesh count, because today I'm using a student version, so we are not getting much more ice frame, as well as I can't run it for more number of time steps, right? And if you want to see an iso surface of the ice also, you can do that. Select the icing, ice thickness, and maybe you can decrease the value. Mm, Display. So these are all the ice formation zones what you can see within that specified time. Okay, and we'll also check the water that has been forming, or what is water that has been getting stuck onto the plane. So maybe we'll select ZX plane or YZ plane. So this might be suitable. So this plane, I think that is suitable. Click on counters, and instead of ice thickness, we'll go and select the uh, water content. Okay, liquid vapor or liquid water that is been on to the plane, and we'll select the plane instead of wall. I'll remove this. So we'll click auto compute range, then you will see. So you can see the formation here. So there is a deposition that is being getting deposited. We'll just again this also we can do in the same way. Instead of maximum value this, we can keep e power -2, and we'll just check everything is e power -2. Then we can do one thing. So you can see the water, how it is being around the section of this missile. Okay, so these are all the this thing, and we can check for the velocity also. Of course this is possible in fluent also, but still we'll select auto range. This is how it is being getting distributed. Okay, and if you want to see the pressures, yeah, everything is possible. Quite, maybe we'll select the wall instead of a plane, and we'll display. So these are the high pressure ranges where it is been getting stuck, and due to this high pressure ranges, so there can be a formation of water that has been getting stagnated those locations. Okay, so please do subscribe, and if you have any queries, you can just check in the mail section. Okay, thank you.